I told you yesterday that that what we were doing yesterday, which was called the first derivative chart, was really the pre-work that we need in order to sketch, which is what we're starting today, and we're going to be doing for a bunch of days. And today we're starting with some pretty easy sketches and just hopefully getting used to some of the format, how we organize our solution, that kind of thing. But then we'll start doing more complex solutions and add a whole nother level of detail to it in a couple of days. But don't forget that yesterday, that question is one that pops up on tests, and it says, determine the intervals of increase and decrease, and determine and classify all critical values as local max, local min, or vertical asymptotes, or whatever. And when we ask that question, we ask it in a way that people don't understand what it's asking and leave it blank. And all it means is find the first derivative chart, which is probably something that almost all of us will be very good at before the end of this unit. So just keep that in mind. Okay, prior to today, from MHF, you could already sketch something like this. What could we already do? We could already find the intercepts. How do I find intercepts of any function, really? But so by factor, that would find me which intercepts? I can find the x-intercepts by factoring and setting it equal to 0 and figuring out where it's equal to 0. Very good. That's probably something that you'll remember to do. What are there any other intercepts? How do you get that? Set x equal to 0. This is one that people forget, or they remember to do it but forget to label it on the graph. I don't know why. Y-intercept is a really nice one to check that your asymptotes and x-intercepts are in the right place. So believe it or not, the Y-intercept is a really good one. Otherwise, you get people doing things like this. They've got an asymptote here, and an x-intercept here, and a y-intercept here, and an x-intercept here. And they go, and then there's another asymptote here, and they go something like, I don't know, or like, or hopefully, I've seen graphs like that, but hopefully you do a little bit better and you would just go like that. But this has what I call a phantom intercept because we never calculated that one. You just included it to try to include this one. Probably what's wrong here is this intercept belongs over here. You know, and it just doesn't belong there. And in that case, you would go whoop, and everything would be fine, and everything would match. And remember, and again, this is a tip from MHF, but it's the same thing here. If you're ever graphing and all of a sudden you're like, huh, that's weird, stop. That's an indication that you've probably made some kind of mistake. Like there's this weird gut feeling that you get when something doesn't match. And to me, recognizing that is like, something's wrong here. And because we're going to add the whole first derivative chart, we've got even more properties that have to match. And so if they don't match, you've made a calculation error, maybe something small, right? And I know it's hard to find those errors, but like go back and see if you can find it, or stop and move on, finish the rest of your quiz or test and come back to it, or something like that, okay? Because things have to match. So the Y-intercept, I have always felt, is a really good one for that. We already know how to find intercepts. Just make sure you have to do it. We also know how to do end behavior. Now, we're going to get added value on the end behavior today. But how do you do end behavior for a polynomial? It's been a while since we've done this. Degree is half of it. Positive or negative leading coefficient. So that's going to help us. Whether it's increasing or decreasing will also help us, because if it's increasing, it can only be coming from one quadrant. And if it's decreasing, it can only be coming from or going to one quadrant. But also, if I was doing a polynomial, I would be thinking about all that good MHF stuff and cross-checking all of my details. So we know what this one's going to do. This one has a positive leading coefficient, and it's even degree, so it's going to be something like that, right? We already know all that. This becomes harder starting tomorrow when we add in asymptotes and we do all of the behavior around asymptotes as well. What are we adding today? We are adding critical values and intervals of increase and decrease. So critical values means turning points and twists. Not only will we be able to find them, but we'll be able to like locate exactly where they are and label them as a point, just like we used to label the vertex of a parabola back in grade 10. So that's what we're adding today. Sound good? Let's get started. These things get big. They'll take one full long piece of paper. In fact, some of you on the test will do your sketch on the back of a full long sheet of test paper. These sketches are a bit shorter, the polynomial ones, but the other ones will take 2 pieces of paper in your notes kind of thing, like they're long. So organization is key, not just for you, but for me, not just for me, but for you. Okay, keeping your stuff organized will help you. It'll help you be efficient and get things done quickly. Doing it in the same order every time is a nice habit. Then it doesn't require you to think as much as you're doing it. You rely on habits to kind of speed things up. But trust me, everybody thinks their own work is easy to read. Everybody thinks that their work is like, oh, I don't know, anybody can follow this. Even if your work is organized, it still can be very difficult. If you do anything that's even slightly different, trust me. When I have to look at 40 or 50 different solutions to a question and they're all slightly different, it's tricky. So the more value you can add to your organization, the easier it is to mark, but it'll help you as well. Okay, so I always do it in the same order, and I kind of give things titles and stuff like that. So I'm going to start with intercepts. Oh no, sorry, I'm not going to start with intercepts. We're not there yet. I'm going to start with all of my derivatives and all of my simplifying all at the top. Okay, so I'm going to factor first. Like you could factor later when you're finding the X-intercepts, but I'm going to do it now. How am I going to factor this? Or how are you going to factor this? So factor theorem, that's one of our options, which you would probably use synthetic division to do. There's an easier way for this one specifically. It's not yet. Yeah, very good. Yeah, this is not a quadratic that we would call it, but it is a simple trinomial. So we factor it as a simple trinomial. And I believe it works out to x squared minus 9 and x squared plus 1. Thank you. Done? No. Still have a different squares. And a sum of squares. Kate's shaking her head like, sir, what are you doing? Oh my gosh, but people do it. That's why I'm pointing it out. That is not factorable, folks. Please don't factor that. It takes years off of your math teacher's life whenever somebody does that. Okay, so that's done. Difference of cubes and sum of cubes can both be factors. Sum of squares cannot be factored. Okay, that one's done. Now, derivative. And I'm going to fully factor that as well. Now, we've got all that pre-work done, all the derivative work done. Now I can move on to start finding all the details and properties to sketch. Were you okay so far? It's funny, every one of these little things that's part of the sketch you already know how to do. I mean, the first derivative chart we just did yesterday, and there's a couple of little details that you haven't seen before just because we haven't done one yet. But all of these, this is just putting together a bunch of skills that you already have. You know how to take the derivative of something. We know how to find X-intercepts and Y-intercepts. We know how to do testing behavior around asymptote. Like we know how to do all this stuff, but putting it all together and doing it correctly in the right order is the challenge. So I always start with intercepts. I'm going to write a little bit extra for this first one so that if we look back at our notes, we remember exactly what we did. There can be some confusion about which function you look at in order to find these things. If you don't know which function you're looking at to find the intercepts, though, you're in a lot of trouble. When you get to the end and we're doing the first derivative chart, if you make a mistake down there, that's one thing. But if you do it wrong up here, that's a bigger problem. So the y-intercepts occur when x equals 0. And that means I'm subbing into the original equation, please. I would normally never show this substitution step. Not only do we want factored form, it's nice to have simplified form. Not just for polynomials, but for rational functions as well, because there's details in simplified form that are easier to pick out. So it's nice to have both of these. If I gave you factored, I would maybe expand it to get simplified. And if I give you simplified, you have to factor. Okay. So this is our y-intercept. And x-intercepts occur when, yeah, thank you, -9, obviously. When y equals 0. So that means, again, still the original function. Not only is this not factorable, but it's not solvable. So there's no x-intercepts there. So I've got 2 x-intercepts and they're plus and minus 3. Intercept's done. Don't forget about the y-intercept. The x-intercepts you'll never forget about. Don't forget about the y one. Label it and remember where it is. Basically, you have to know if it's positive or negative, but remember that. Okay. Next, we do asymptotes. We don't have any asymptotes but we will tomorrow. So now I'm going to look at critical values. If you jump to when the derivative equals 0, you're probably going to forget to think about when it does not exist. So we always start with where it does not exist first. It's often a bit easier. Maybe that's not true, but I think it's a good habit. For polynomials, it's trivial. Polynomials exist everywhere. The derivative of a polynomial is always a polynomial. So the derivative will always exist everywhere. Which means, whoops, all I have to do is make this statement. Now exists for all x. Now I can be done and move on and forget about it. Okay? You'll see this tomorrow, but if you have critical values where the derivative does not exist, they go into your derivative chart. They're part of the derivative, the first derivative chart. Okay. Now we're going to do where f prime equals 0. And again, we've already done the work for it, so it's trivial. I would usually just state it, but in this case, I'm going to write it out. So this is where 4x, x plus 2, x minus 2 equals 0. So for where x equals 0 and plus or minus 2. What do you think we do next? Put it all into our first derivative chart, same as we were doing yesterday. So I am splitting up these intervals of my critical values, starting with the smallest. And then we have to consider that value as well. You can't skip having the -2 there. And I'm going to put in these. And again, if it was where 1 does not exist, I would write that DNE, not 0. Now I'm doing the testing. So if I take -10, that's in the first interval. I probably don't have to say this, but I will because I don't know that I've said it yet. I'm sure, I'm sure I did in MHF, but -10 is not always in that first interval. If you had a critical value that was less than -10, you can't just always use -10, right? But often you can. But every once in a while you get somebody who just thinks you always use -10. But it is in the interval, so negative, negative, negative. So that one's negative. Some people think the second value always uses 0. That wouldn't work because if I put it in, I'd get 0. You'd think, oh, that's positive, so that one's positive. No, 0 is not positive. It's not negative. It's neither. So I have to use a value in this interval, so I'll use -1. I got negative, positive, negative. 2 negatives makes positive. Then I'll use 1, and I get 1 negative. Then I'll use 10, and I get no negatives. We okay? So this is decreasing, increasing, decreasing, increasing. So if I'm decreasing, and then I'm 0, and then I'm increasing, I have a local min. So both of these are local mins. And the other one's obviously the opposite. I'm increasing, 0, decreasing. So that's a local max. One new step today. We need to actually find the y values associated with those points because we want to know exactly what those points are. So and this is where I could see people making more mistakes. But this is now going back into the original function. This is a point on the original function. It's a local minimum on the original function. So I go f at 2. And I plug it in, and I get -25. So this point is -2, -25. And I like to label them. But that's a personal preference. F at 0 is, well, -9. We already know that. That's our Y-intercept. And f at, well, that should say -2. And f at +2 happens to also be -25. So now I've got point B. This local max is point B, 0, -9. And this will be point C, 2, -25. There are different ways of organizing your solution. So if you're looking at solutions online, there happen to be some old solutions from a few years ago or a different teacher or something like that. They might be organized slightly differently. It's not particular about exactly how you organize, just that it is organized and easy to read. So I tend to do my points in the chart like this. I don't usually show that step, by the way. I just do this. There's no need show that, right? This is just for our note today. But you got to put these points somewhere. If you label the points directly on the graph, that's fine. Sometimes it muddles it up, so that's why I use letters. Looks to me like it's going to be, yeah. It's not always, but this one sure looks like it. Yeah, definitely. All right, we good? What do you think? I think we're ready to sketch. Again, the exact order in which you sketch doesn't necessarily matter. I think there's kind of a natural progression, but that's up to you. You probably have to draw your axes first. That would be weird if you drew your axes in at the end. But you know, you get your axes done, and then you just start putting stuff in that you know, putting in your intercepts, putting in your asymptotes, whatever you have. Maybe thinking ahead about how to spread it out. I happen to know this one, keeping our X-intercepts out a little bit wide, not too crunched in, will help. So don't put 3 in here, -3 in there. So I'm going to put -3 over here, and +3 over here. Oh, that's what I was going to say. Definitely we're not graphing this on graph paper. Good luck doing that. Okay. So it's just a sketch. And then I've got my Y-intercept of -9. And I also have these values at -2 and +2 at -25. So I'm going to mark that. And I'm going to come here and I'm going to find about where 2 is. It's not perfectly symmetrical, but that's good enough. So I'm going to have a point here. And a point here. Nope, here. And that's my other point. Putting it all together, we start decreasing. And we already know that this is degree 4, positive leading coefficient, so the end behavior has to look like this. So that makes sense that I would start decreasing like this. Local min, local max, local min, and then increasing in the end. Last thing is where I label my points. A, B, C. So like I said, that's just how I do it. You could label the points right on the graph if you want, but it can get jumbled up. Questions? Ready for one more? Complete a fully labeled sketch of the function below showing all intercepts and critical values and intervals of increase and decrease. You kind of have to anyway, but okay. Basically, when you're asked to sketch, you're supposed to use all of the detail that you can. Everybody good? Ready to start? So I'm going to start by factoring this. And I made a mistake already. There we go. Then derivative. So go ahead. And I'm going to factor that as well, just to get all of that out of the way. All right, let's do intercepts. What's my y-intercept? Oh, 0. Because there's no constant, right? So 0. That's why it's nice to have, again, I think I said this, but it's nice to have the factor form and the simplified form. X-intercepts, I'm going to show this one again. So for the x-intercepts, x cubed is x squared minus 15 equals 0. Because this is not factorable, technically, because it's not 15 is not a perfect square, but it is solvable. So there's two intercepts there. If you didn't notice them, well, I just blew something. Whoops. That's okay. So there's two intercepts, and if you didn't find them, you'd start sketching. You'd be like, what's going on here? Hopefully, you'd catch it. Okay, so that means x cubed equals 0. So x equals 0, or x squared minus 15 equals 0. So x squared equals 15. So x equals? Thank you. Plus or minus square root of 15. If you missed one of those, that would not work either. Happy with that? Yeah? Critical values. Again, it's polynomial, so it exists everywhere. So where does it equal 0? Now I'm looking at the derivative. Looks like 0 and plus or minus 3. Now, what do we do next? Very good. First derivative chart. So go ahead. This is what I have so far. Hopefully you got that and you can start doing your testing. Now be careful. When my first interval is x is less than -3, so I can use -10. -10 squared is a positive. In fact, no matter what you put into this first part, it'll always be positive. So I don't really have to think about it if I don't want to. So this is negative and this is negative. Two negatives makes a positive. So this first one is positive. Then I'm going to pick -2 for this next interval. And I'll pick +2 for the next one, probably. So where am I going here? So -2, again, this one's positive. This becomes positive, and this one's negative. If I have -2. And if I put +2 in there, I get positive, still negative. And the last one, everything's positive. If you take it for granted that it always flips back and forth, be careful. It does not. Okay, so this is increasing, decreasing, decreasing, increasing. If I'm decreasing and then increasing, that's a local min. If I'm increasing and then decreasing, that's a local max. What is happening if I'm decreasing then decreasing? Yeah, it's going to be a twist, which we are going to call a horizontal tangent line. The other ones are horizontal tangent lines too, just they are also local extremum. Okay, I got to find these values. So I'm going to plug them in, and this one is -3 and a positive 162. One of the reasons why these would be hard to do on graph paper. This one we already know because it's an intercept. It's 0, 0. There's a lot going on at that point. And this one is positive 3, negative 162. Okay, and like last time, we start putting details on. I probably want to know the approximate value of the square root of 15. Those are X-intercepts. It's 3.9, plus or minus 3.9, right? And somewhere I need negative 162 and positive 162. I'm going to have a point at 0. This one was degree 5 positive leading coefficient, so it's going to start in quadrant 3 and go to quadrant 1. And it starts increasing until x hits negative 3, where we have this point. So again, that matches. And what's happening? Remember what's happening at this next point here? It's a twist. So keep that in mind when you're graphing. And then I have my local minimum. And then it goes from there. Any questions?